Hello everyone. Today we are going to analyze this frame using flexibility matrix method. Before analyzing, let us see the frame one time. In this frame, there are two columns, column AB and column DC. Also, there is a beam BC. In the columns, there are no loads. In the beam BC, there is an eccentric point load 18 kN acting at a distance of 2 meter from the point B. The length of the columns is 4 meter. Length of the beam BC is 6 meter. The moment of inertia for the columns is given as 3I. The moment of inertia for the beam is given as 1.5I. In this frame, the number of unknown reactions and moments is 6. They are VA, VD, HA, HD, MA and MD. The available equilibrium equations are 3. Sigma m is equal to 0, sigma v is equal to 0 and sigma h is equal to 0. The degree of static indeterminacy is equal to 6 minus 3. We will get 3. From the point D, let us remove MD, HD and VD. In the point D, there was a fixed support, but when we release these three reactions, the fixed support is removed. So after releasing these three reactions, the point D is a free end. This structure is called the released structure. Now let us make the coordinates diagram. In this analysis, there are three coordinates. I am keeping the vertical support in the point D as the first coordinate, the horizontal support in the point D as the second coordinate, and the moment in the point D as the third coordinate. We are keeping them as the coordinates because these are the reactions we have removed. Let us keep the vertical reaction upwards, the horizontal reaction towards the right side, and let us keep the movement in the clockwise direction. Finally, if we get positive values, our assumptions are correct. If we get negative values, our assumptions are wrong. Then we have to change the directions. Let us see the formula to find the final answers. P matrix is equal to delta matrix inverse into delta matrix minus delta L matrix. Inside the P matrix, we will have the reactions VD, HD and the moment MD because these are the reactions we have removed. Inside the delta L matrix and delta matrix, there will be three values because in this analysis, there are three coordinates. In the given frame, in the point D, there is no settlement or rotation. So, inside the delta matrix, we can simply enter 0, 0 and 0. The size of the flexibility matrix will be 3 cross 3 because in this analysis, there are three coordinates. In this formula, we have found delta matrix. Now we are going to find delta L matrix and delta matrix. For that, we are going to apply unit load method. In the unit load method, first we have to find the moment m. Using the load in the frame, we have to find the moment m. Then we have to remove all of the loads and apply unit load in the first coordinate and then find the moment m1. Then we have to apply the unit load in the second coordinate and find the moment m2. Finally, we have to apply unit moment in the third coordinate and find the moment m3. First, let us find the moment m. For finding the moment, we have to make sections. In this frame, there are 4 different parts: DC, CE, EB, and BA. So we have to make 4 sections. I have made the first section in DC, the second section in CE, the third section in EB, and the fourth section in BA. Before finding the moments in the sections, let us make the free body diagram so that we can easily find the moments in the sections. I am going to split the frame from the point C and B so that I will get 3 different parts. You can see that I have split the frame into 3 different parts: DC, CB, and BA. In DC, there are no loads. In BC, in the point E, there is a point load 18 kN. Because of this point load, a reaction is created in the point B. Since the load is acting downwards, the reaction should be acting upwards. Now let us find the moment in the point B. This load is acting in the clockwise direction and the distance is 2 meters. 18 into 2, we will get 36. Since this load is acting in the clockwise direction, the developed moment in the point B should be acting in the anti-clockwise direction. Now let us take the portion BA. On the right side in the point B, the reaction is acting upwards. So in the left side, it should be acting downwards. On the right side, the movement is acting in the anti-clockwise direction. So on the left side, it should be acting in the clockwise direction. Let us take the member DC. In DC, I have made the section at a distance of x from the point D. So for DC, the origin of the section should be D. The moment of inertia for DC is 3I. So the flexural rigidity should be 3EI. The limits for DC is 0 to 4. Now let us take CE. In CE, I have made the section at a distance of x from the point C. So the origin of the section should be C. The limit is 0 to 4. Now let us take EB. In EB, I have made the section at a distance of x from the point C. So the origin of the section should be C. The limit is 4 to 6. For BC, the moment of inertia is 1.5I. So the flexural rigidity for CE and EB should be 1.5 EI. Now let us take BA. In BA, I have made the section at a distance of x from the point B. So the origin of the section should be B. The limit is 0 to 4. The moment of inertia for BA is 3I. So the flexural rigidity should be 3EI. Now we are going to find the moment M. We are going to find the moments towards the left hand direction. In this case, clockwise will be negative and anti-clockwise will be positive. First, let us take DC. In DC, up to the section, there is no load, so the moment will be 0. Let us take CE. In CE, up to the section, there is no load, so here also the moment will be 0. Now let us find the moment in EB. In EB, up to the section, we have a load 18 kN. This load is acting in the clockwise direction, so it will be negative. For the distance, we have to take this distance. This distance is x minus 4. Then we can multiply minus 18 with x minus 4. When we do that, we are getting this. Let us apply that. Now let us find the moment in BA. For this load 18, there is no perpendicular distance, so we can't consider that. This movement is acting in the clockwise direction, so it will be negative. Now we are going to find the moment M1. For that, we have to apply unit load in the first coordinate. Now let us make the free body diagram. Because of this unit load, a reaction is created in the point C. The unit load is acting upwards, so the reaction should be acting downwards. In the point C, on the right side, the reaction is acting downwards. So in the left side, it should be acting upwards. Because of this, a reaction is developed in the point B. Since it is acting upwards, the reaction in the point B should be acting downwards. Now let us find the moment in the point B. This load is acting towards the point B in the anticlockwise direction and the distance is 6. 1 into 6, we will get 6. Since this load is acting in the anticlockwise direction, the developed moment should be acting in the clockwise direction. In the right side, in the point B, the reaction is acting downwards. So on the left side, it should be acting upwards. On the right side, the moment is acting in the clockwise direction. So in the left side, it should be acting in the anticlockwise direction. Now let us find M1 in DC. In DC, up to the section, we have only the unit load. For this unit load, there is no perpendicular distance, so we should not consider that. In this case, in DC, M1 is 0. Now let us find M1 in CE. This unit load is acting towards the section in the anticlockwise direction, so it will be positive and the distance is x. 1 into x, we will get x. Now let us find M1 in EB. This unit load is acting towards the section in the anti-clockwise direction, so it will be positive and the distance is x. 1 into x, we will get x. Now let us find M1 in BA. This movement is acting in the anti-clockwise direction, so it will be positive. Now we are going to find the moment M2. For that we have to apply unit load in the second coordinate. Now let us make the free body diagram. Because of this unit load, a reaction is developed in the point C. Let us find the moment in the point C. This unit load is acting towards the point C in the anti-clockwise direction and the distance is 4. 1 into 4, we will get 4. Since this load is acting in the anti-clockwise direction, the developed moment should be acting in the clockwise direction. Here in the point C, the unit load is acting towards the left side. So here it should be acting towards the right side. Here towards the left side and here towards the right side. Here the movement is acting in the clockwise direction. So here it should be acting in the anti-clockwise direction. Here clockwise direction and finally here anti-clockwise direction. Now let us find M2 in DC. This unit load is acting in the anti-clockwise direction, so it will be positive and the distance is x. 1 into x, we will get x. Now let us find M2 in CE. This movement is acting in the anti-clockwise direction, so it will be positive. Now let us find M2 in EB. This movement is acting in the anti-clockwise direction, so it will be positive. Now let us find M2 in BA. This movement is acting in the anti-clockwise direction, so it will be positive. This unit load is acting in the clockwise direction, so it will be negative and the distance is x. 1 into x, we will get x. Now we are going to find the moment M3. For that we have to apply unit moment in the third coordinate. Now let us make the free body diagram. In the point D, the unit movement is acting in the clockwise direction. So here it should be acting in the anti-clockwise direction. Here clockwise direction. Here anti-clockwise direction. And finally here clockwise direction. Now let us find M3 in DC. This unit movement is acting in the clockwise direction, so it will be negative. Now let us find M3 in CE. Here the unit movement is acting in the clockwise direction, so it will be negative. Now let us find M3 in EB. This unit movement is acting in the clockwise direction, so it will be negative. Now let us find M3 in BA. This unit movement is acting in the clockwise direction, so it will be negative. In this formula, now we are going to find delta L matrix. In delta L matrix, first we are going to find delta 1L. The formula is integration of m1 upon ei dx. For DC and CE, the value of m is 0, so no need to make the integration. For EB, the limit is 4 to 6. The flexural rigidity is 1.5 EI, so instead of EI, we have to apply 1.5 EI. For BA, the limit is 0 to 4. The flexural rigidity is 3 EI. So instead of EI, we have to apply 3 EI. In the formula, let us apply the values of M and M1. Now we can use the calculator and do these integrations. If you do not know how to use calculator for the integrations, see the description below. There is a link. You can click the link and watch the video. I have used the calculator and got these values. After adding these two values, I am getting delta 1L, which is equal to minus 416 upon EI. Now let us find delta 2L. The formula is integration of m2 upon EI dx. Let us apply the values of m and m2 in the integrations. After the calculations, we are getting delta 2L. Now let us find delta 3L. The formula is integration of m3 upon EI dx. Let us apply the values of m and m3 in the integrations. After the calculations, we are getting delta 3L. In the delta L matrix, we have calculated all of the values. Let us apply them. 1 upon EI is constant. Let us keep it outside. In this formula, now we are going to find the flexibility matrix. In the flexibility matrix, first let us find delta 1, 1. The formula is integration of m1 square upon EI dx. In the formula, let us apply the values of m1. After the calculations, we are getting delta 1, 1. In the flexibility matrix, now let us find delta 1, 2 and delta 2, 1. Both of them having the same formula, integration of m1 m2 upon EI dx. Let us apply the values of m1 and m2. After the calculations, we are getting delta 1, 2 and delta 2, 1. In the delta matrix, now let us find delta 1, 3 and delta 3, 1. Both of them having the same formula, integration of m1 m3 upon EI dx. In the formula, let us apply the values of m1 and m3. After the calculations, we are getting delta 1, 3 and delta 3, 1. In the delta matrix, now let us find delta 2, 2. The formula is integration of m2 square upon EI dx. In the formula, let us apply the values of m2. After the calculations, we are getting delta 2, 2. In the delta matrix, now let us find delta 2, 3 and delta 3, 2. Both of them having the same formula, integration of m2 m3 upon EI dx. Let us apply the values of m2 and m3 in the formula. After the calculations, we are getting delta 2, 3 and delta 3, 2. In the delta matrix, now let us find delta 3, 3. The formula is integration of m3 square upon EI dx. In the formula, let us apply the values of m3. After the calculations, we are getting delta 3, 3. In the delta matrix, we have calculated all of the values. Let us apply them. 1 upon EI is constant. Let us keep it outside. In this formula, we have found all of the values. Let us apply them. 1 upon EI inverse is equal to EI. we have to add these two matrices. After adding, we are getting this. For this matrix, we have to find the inverse. We can apply all of the values in the calculator and get the inverse. If you do not know how to find inverse in the calculator, see the description below. There is a link. You can click the link and watch the video. I have used the calculator and got the inverse. Then we have to multiply these two matrices. After multiplying, we are getting this. For VD, we got a positive value. That means our assumption is correct. For HD and MD, we got negative values. That means the assumed directions for both of them are incorrect. We assumed that MD would be acting in the clockwise direction, but we got a negative value. That means our assumption is incorrect. MD is actually acting in the anticlockwise direction. Also, we assumed that HD would be acting towards the right side. Since we got a negative value, actually it is acting towards the left side. Now let us apply the rule sigma h is equal to 0 and find out HA. Now let us apply the rule sigma v is equal to 0 and find out VA. Let us assume that MA is acting in the clockwise direction. Let us take moment about A and find out MA. Since we got a positive value, our assumption is correct. MA is acting in the clockwise direction. Now we are going to draw the shear force and bending moment diagrams. Before drawing them, we can make the free body diagram. If we make the free body diagrams, it will be very easy for us to make the shear force and bending moment diagrams. Here you can see the shear force diagram. Here you can see the bending moment diagram by superposition method. Now we are going to end this session. Thank you for watching this video.